All right. So next we have our first invited speaker for this session. He also happens to be my colleague at Deakin University. He's Richard Dazeley, and he heads the Machine Intelligence Lab here. Richard has mainly published a whole body of work in multi-objective reinforcement learning. And he is also working on interactive, safe, and explainable reinforcement learning. So the topic of his talk today is Broad-XAI, human-aligned conversational explanations. So Richard, if you're ready, you can take over.
Thank you. I'm just sharing my screen, hopefully.
Sure.
How's that? Does that come through?
Yeah, we see
awesome.
It.
Okay. So thank you for the introduction, Tom, and thank you everybody for joining, and thank you for the invitation to the committee. As introduced, a lot of my work in the past has been around multi-objective reinforcement learning. Probably the last 13, 14 years has been around that area. So that work has been done with Peter Vamplew, and Peter did a nice introduction earlier. So I've kind of kept some of that out of my talk today, even though it is part of it. I don't want to re-go over the background, but I guess while a lot of our early work had been sort of, let's say, foundational work within that space, we're some of the first people to work in that space, we've sort of realized over the last few years how applicable it is within the human-aligned problem domain, and in helping HARL be able to interface with humans in this aligned domain. And so we started working in this area. So we've been working in a couple of different spaces. One of them, Peter talked earlier about safe RL and impact minimization. And so the work that I've been focusing on has been more around the explanation side. And in particular, I guess something that I've seen as a bit of a deficiency in some of the some of the explanation work is around the current approach to explanation is very much around debugging. So hopefully those slides are clicking through. So a lot of XAI work at the moment, not necessarily all of it, but a lot of it is very much sort of debugging explanations. So somebody comes up with an algorithm and then they try and come up with a way of interpreting that algorithm. And this is not necessarily particularly useful to lay people. I mean, we wouldn't use a debugging message from our code to explain why their program isn't working. Yet at the moment, the majority of XAI work is sort of looking at this debugging side. So I think there is a lot of room in explainability to be able to look more at the user side and making sure that those explanations align to what a user can actually use. And it's very much still an unsolved problem. So this particular paper that I'm mostly focusing on, although I'll touch on a second paper as well, is a bit more of a philosophical style of paper. It's not, we don't actually propose any algorithms particularly, but it's looks at the literature and discusses how we can actually approach the larger problem of addressing explanations for lay people. So one of the things that we argue in this paper is that an explanation actually needs to align to the explanee's current position, their contextual position. So what their current understanding of the world is. And to do that, we suggest that this is done through an interactive process. So in order to find what their current contextual position, what it is they actually want to know, we need to actually go through a process to get to that. And that interactive process we've referred to as a conversation. So a conversation isn't necessarily like a conversation between two people, which is generally vocal. Conversation just means an interaction. So that could be through some sort of visual means. whether not that's sign language or semaphores or images or whatever. It can also be audio or text. But it's about trying to narrow in on what the explanee is actually trying to find out in their question. And the reason why that's particularly hard, if you look at current explainable work, which is primarily explaining a single decision based on a single algorithm. So if you think of an image classifier, you might ask it, well, how did you come to that conclusion? It will point to the cat in the image and say, this is what I was looking at, and that's why I classified it as cat. That's fine for simple AI, but once you start talking about integrated AI systems, that sort of simple approach won't cut it anymore. And we actually need an approach to explainability that handles that integrated experience. Now, we've coined the term Broad-XAI, so sort of a broad-based explanation. It's not going to be able to cover all the elements in the decision, because providing too much information to a user is as useless as providing none. You overburden the explanee. So you need to actually filter the amount of information and make sure that you're providing the right level of information for that particular person. In order to do this, we actually need to understand what the different levels of explanation actually are. So a lot of this paper was actually around what are the levels of explanation. And if you consider psychology has defined some levels, although AI hasn't, apart from today's paper. But in psychology, they'll often talk about sort of the socio-cultural level of explanation. So this is where somebody's explanation is, I did this because this is sort of the society rules, or that I did this because of the situation that I'm currently in that room. So I held the door open because social convention says I should hold the door open for someone that's coming in after I've already passed through the door. But then there's also explanations that are at the personal level, at that lower level. So I did a particular action. I kicked the ball because I'm trying to score a goal or something. So there's this thing that I'm trying to do, or a biological level of I did something because I was hungry, or because I hadn't had my coffee yet in the morning, or whatever the internal chemical or biological reason that might have been driving that action. Humans are primarily a social creature, whereas an AI is not. And we need to be able to pair up an AI's cognitive process, which is primarily data-driven, to that of the human's socially driven cognitive process. And that's kind of what the models that we're trying to portray here are looking at. So just a brief example of an integrated AI system might be, say, an autonomous car. And I'm just going to use this as an example throughout this presentation before I run out of time. But if you think back, many of you will remember there was an Uber car accident back in 2017 where a pedestrian was struck. And it actually took about 6 to 12 months of analysis as into this accident by various computer scientists and so forth, analyzing logs to be able to find out why the system had behaved the way it had. Whereas generally, we actually want an integrated system like this to be able to provide an explanation to us straight away, and that explanation should be sort of meaningful to the person that I am and the type of information that I'm actually looking for. So perhaps in this particular situation, the car may have provided an explanation such as, I didn't recognize there was a person pushing a bicycle. That would certainly tell you why it hadn't stopped, because it hadn't seen the person. But it might also likewise describe something such as the motivation for staying in the right-hand lane was because there was an exit coming up here on the right, and so they wanted to the car wanted to stay in the right lane. Or perhaps when it saw the bicycle over on the left, it believed that the person was going to give way, so it continued on. Or maybe it believed that it had right of way, and so it should continue on, or the person would expect them to continue on. Of course, the reason may actually be a traditional fault, and the eventual finding of this was that it was a user setting. The driver had set it to not do emergency braking, and so the person had been detected, but it couldn't brake because it was set not to. But in this particular case, the utility or the ultimate goal of the integrated AI is to provide an explanation for this. So a simplified abstraction of this is that you've got these external environment features such as other actors, cars, pedestrians and animals, etc., as well as some static features such as trees and buildings and so forth. And you need to perceive these particular items so that your AI can make a decision. So you receive these inputs, you extract some features, your AI makes a decision based on that. Now, this AI might make that decision just by reacting to what it's seen, but it might also incorporate some other information that it's built into the AI, such as a memory of past events so that it remembers what's happened before, a model of, say, a pedestrian's behaviors, so what it thinks pedestrians might do, what it thinks other cars might do in certain situations, other parameter settings. These internal motivations might also be things like emotions and so forth in certain social robot type situations. So you've got this internal model, if you like, of the AI agent that the AI agent uses to help make those decisions. We need to be able to generate explanations that incorporate all of these things. So we came up with a set of levels for explanation, which are here on the screen. And these are very much based on animal ethology's approach to explaining animal behavior. So animal ethology looked at the levels of intentionality of animals to explain what they're doing. So if we sort of step through some of these, we've got zero order explanations. These are purely reactive explanations. So in an animal sense, such as a monkey, it might see a snake in the ground and immediately climb a tree to get away from the snake. That is an immediate action responding to fear of that snake. Now, in the AI sense, this is very much most of current explainability work. So if you look at saliency maps, classification, explanation systems, they're primarily taking a input data and processing that and producing an output. The explanation of that is how it got that output from that particular piece of data. So it's literally looking at the input features and the AI process to develop that. And it allows you to answer simple explanation questions such as what are the input features that were important when making the decision, as well as counterfactuals such as what if certain features were changed, what would the decision be? But these are still very much reaction-based explanations. The next level up looks at the first order when there's a single order of intentionality behind the agent. So what was the motivation of the agent? And this is where, and if you have a look at that original model, this is very much an HARL model of an environment. We've got an agent making a decision, and that environment, that decision affects the environment, etc. But when we look at the disposition or this first order intentionality, we're going, well, what was the goal of the agent? What was the purpose? Was there an emotion that was driving that decision? Was there certain parameter settings? In the RL sense, perhaps we've got a hierarchy of goals. So which is the current goal we're seeking? I come from a multi-objective point of view. So what was the current objective that we're following? What was the weighing up between those objectives in making that decision? And this provides a lot more information to the agent and allows us to answer sort of more sophisticated questions such as why did you want to be in that lane in particular. Second order explanation, which is paralleled to second order intentionality, is instead of what was the agent's intentions, it looks at what was the other actors in the environment's intention. So it's trying to, the idea is the model, the AI has got a model of the other actors' behavior. So if, for instance, you look at pedestrians, what do I expect that pedestrian to do? And how did that affect my decision in a particular case? So for example, autonomous car is driving along, it observes a child chasing a ball and that ball rolls out onto the road. The car may decide to slow down. Now the driver, if they ask, why did you suddenly slow down? Its response is, because my model of that, it wouldn't probably say model, but because of that model of the pedestrian, it's predicted that there is a risk that that child might run out onto the road, and so it's taking this precaution to slow down. And it allows you to answer much more sophisticated questions and get more sophisticated answers, such as I slowed down because the pedestrian approaching the intersection appeared intent on crossing. So it's made a prediction about the intent of the other person's behavior. Intentionality actually continues up and up. This model actually only looks at the nth level. So we've called this cultural level. And this is what does the other agent, what does the other person expect or expect my intentions are? So it's a prediction of what they think we are going to do. It's actually important that an AI actually considers this because, for instance, if a car is driving along, you can't just have the car suddenly hit on the brakes for no apparent reason because the other cars aren't expecting that. So you actually, what the other cars are expecting is an important component for that decision making as well. So you can't change behavior rapidly. One example that I used in this paper was you're walking through a shopping center and somebody's walking directly towards you. Cultural rules in some countries, such as Australia, might be that you take a step to the left, they will also take a step to the left, and then you'll miss each other when walking past. But when going to another country, perhaps one where they drive on the right-hand side, if you step to the left there, they may step to the right and may cause a collision. So there's a lot of cultural rules that might be built into this sort of behavior. And again, this allows quite a lot more sophisticated explanations, such as I didn't slow down for a pedestrian because road laws state I have the right of way, and I assumed that they expected me to continue. Am I going for time? 15 minutes in. So we also were concerned about other aspects. So a meta explanation. So our model also includes this orthogonal concept of meta explanations. This isn't actually a particularly new one. Meta explanations has been around in the literature. But it's an explanation detailing the process or factors that we use to actually generate or infer our actual explanation. So this is, if you like, explaining the explanation. Why is this important? One of the things, when you're looking at purely interpreting an AI, there's no intention behind the explanation. You've got an image, you're simply identifying the area that was processed. The explanations are simple, you can present most of the information required. When you're dealing with these complex integrated systems and the explanations associated to them, you need to simplify the explanation. You can't provide all the information in one hit because it's too much information for the explanee. As soon as you start removing aspects of the explanation and simplifying the explanation, there is a risk that you're going to provide an explanation that's not entirely accurate. because you've simplified it too much or you've generalized something in some way. And so it's actually a major concern that mostly the literature is overlooked. But if we can't trust an agent's original decision, then how can we actually trust the agent's explanation of that decision? So what I've been suggesting in this is to move away from sort of the engineer's explanation and actually look at sort of user-centered or the explanee-centered explanation. And it raises sort of three main areas of difficulty. One is, how do you do this user modeling? Now, one obvious way is to have sort of a utility-driven explanation, which is my explanation is successful when the person receiving my explanation is satisfied with it, that they've accepted my explanation, of which my utility is the acceptance of the user. Now, that doesn't necessarily mean that the explanation I provided is truthful or accurate. It just means I've provided an explanation that they're happy with. And so there's risks with these ideas of utility-driven explanations. Same, there's the potential also for intentionally deceptive explanations. So these are explanations where the point of the explanation is actually to deceive you. And this can come about from utility-driven explanations, but they've actually been, there are quite a number of papers in the area of deceptive explanations where a systems is actually trying to provide an explanation that, for instance, the company likes, not necessarily what the customer likes. So, for instance, a automatic bank loan application is not going to provide the explanation that I didn't give this loan to you because of your race or gender or some other reason that's inappropriate, even though that might actually have been the reason. It's going to want to provide a more an explanation that's not going to upset the customer. And so you've got these potentials of providing deceptive explanations, and they can come about simply because of simplifying and generalizing explanations. So to sort of counter this idea, we've got this meta explanation, which allows the system to explain how it's generated that. So perhaps providing if somebody's requested this, you'd need to be able to provide what the other potential explanations were that could have been generated. All of these are primarily areas that we see as fields of research that need to be pursued, and a lot of them are not being pursued, or at least not being pursued very much. So we've got a list here of areas of explanation. Now, many of these, such as memory aware, emotion aware, and socially aware, there are one or two papers that touch on it, but these are primarily not looked at in the literature very much. So there is a lot of space within explainable AI where we can sort of be looking at these things and providing, there's a lot more research that's possible in these areas. Same with utility driven, there's little bits and pieces, but not very much. So if you have any interest in those, have a look and look up some of those references that we did find for some of these things. Some of these papers didn't necessarily use these terms, but it is actually what they're doing. Okay, so in the terms, they've often just called themselves XAI, but they're actually working in that space. So how does this sort of work within reinforcement learning? It's the focus of this particular paper. So human-aligned reinforcement learning, I guess our view is that it investigates this nexus between autonomous RL systems and how they interact with people in a sort of a mixed domain. And so I guess the area that we've primarily been looking at in our work is you've got an RL agent, it's got some sort of goal that it's trying to achieve, but there's other factors that an RL agent might actually consider, such as safety aspects, which Peter talked about earlier, ethical aspects, interactive aspects, behavior of other users within the people or agents within the environment, and how they're all actually interacting with each other. Now, in this particular diagram, I've specifically chosen gears and given direction to these gears that show that they will not work. These are all in conflict with each other. And so there needs to be a weighing up between these things. The whole idea of this is that this can be done through multi-objective RL. And explainability through a multi-objective lens is what I guess my work is primarily focusing on. So trying to explain the interaction between different components and how they create this final outcome. So in another paper, not yet accepted, currently under review, we've specifically looked at a framework that allows us to do this within reinforcement learning. So we've called this the causal explainable reinforcement learning framework. And this has been derived from various psychology studies on how humans expect things to be explained. And so they actually did a study of the kinds of things people expect in an explanation and the causal relationship between those items. And while I don't have time to go through that study, it directly relates to, this is using RL terms to a certain extent, but it's actually a direct translation of that model. And it translates perfectly to a lot of ideas within RL. And so the idea is you've got some sort of outcome. This is the sink of this graph, is the outcome of the decision. But leading up to this action, this outcome, there might be some action. That action may have been controlled by some sort of goal or objective of the agent. That goal or objective is selected by the internal disposition. So I'm in a hurry, so therefore my objective is the goal is to optimize for time because I want to get to where I'm going as fast as possible. So that's the basis of the objective that I'm focusing on at the moment. So the policy I've selected in the multi-objective sense might be time. Alternatively, if I observe something, if there is an event that occurs, I might realize that I need to switch my internal policy to a safety one. And so my objective will now become a safety objective because I've observed an event. There's also a question of what you actually perceive and how that affects it. And the expectations that we've modeled based on what we expect other agents to be doing. So these links, these arrows indicate the causal link between these that you include in your explanation. The color of these represents the level of that explanation from the set of levels. So the 0 level, the reaction-based, is what I perceive, the action that I took based on that perception, and then what the outcome was of that, what the classification, what the action was at the end. But when you start looking at intention, you're looking at what my current goal was, or what the social events were that were occurring, what was occurring in the environment, or what the expectations are, cultural expectations that I expect to have on my behavior. And so the idea is that you explain by drawing from these links in much the same way as you did from the levels. I think I'm pretty close to out of time. So as part of this, we developed a conversational explanation model, which basically says we start off with a question that somebody is asking. We address any assumptions that might occur. We provide an explanation that either addresses the assumptions or answers the questions. And if the explanee is happy with that, either by they've said they're happy, or they've shown they're happy in some visual way, then that's the end of the process. But what often may happen is we might realize the person isn't satisfied with that explanation, that they don't understand quite yet. And so we'll actually drill down further. So we can actually internally ask the next level down and move the next level within our hierarchy and provide the next explanation that we can generate. And we keep going deeper down the levels from the top down to the bottom until we've actually addressed what they want to know. So just as a bit of a walkthrough to finish off with, you might ask a question, why didn't you give way to the pedestrian pushing a bicycle? This has an inbuilt assumption. The assumption is that there was a pedestrian pushing a bicycle and that the agent was able to perceive that. So the first thing that the agent needs to do is decide whether or not that assumption is actually valid. And so looking at the perception, did it actually perceive a person pushing a bicycle? And if it didn't, then it would provide an explanation saying that it hadn't. And so this would be an explanation from that perception level, which is actually the bottom level, but it was able to jump there from this assumption in the question. If the assumption is valid and it did perceive the bicycle, then it simply starts at the highest level. So if it did detect, then start at the expectations level. And at the expectations level, it may reply with the car might reply that it believed that it had the right of way and that the person would expect the car to continue. One thing that's nice about this is that it's already also simultaneously explained that it did see the pedestrian, because otherwise it wouldn't have reached this explanation. So you're kind of including this other explanation within this higher up explanation. But if the person is still not satisfied with this, then it can essentially ask another question. So they might ask the other question, or it might just simply drill down to the next level. So did the pedestrian show any sign that they intended to give way? And so then the agent can then drill down and have a look at the events type category of what it actually perceived about the agent's intentions. So some work that we've been doing in this, we've got some projects with the United States looking at explaining in a multi-agent framework. So this is a system where an agent is interacting with human agents and possibly other AI agents, and it needs to be able to explain strategies that it's using. So it's both predicting what other agents are doing, so it's got to model what other agents are doing, while being able to explain its changes in behavior based on those other agents. We're also doing work on the adversarial intention of systems. We have a project that's actually trying to implement aspects of this particular framework here around human-centered computing. So a general project, but it's implementing different stages of that. So we've had a couple of papers. Francisco, who's with us earlier, he's done a couple of papers in this area with me. We're also doing some work in apology, which I find interesting because in order to do the apology, which is sort of an extension of explainability, you need to identify the causal reason that maybe the agent did something that's caused a problem, and explain that you realize this and you're sorry that you've done that, and then change your behavior in the future. So it actually provides a way, an interactive approach to be able to select your Pareto policy from a multi-objective domain. And so this sort of extends the impact minimization work that we've been doing. And we're also looking at another defense project around generating narratives, so that where narrative is also a form of explanation. So you're telling a story based on things that have occurred. So it's a bit more of an expanded view of explainability. I won't go back over that because we're over time and I think it's questions. We've had a few papers in the last couple of years around this topic. We also do quite a bit of work around assisted HARL as well. So it's persistent policy shaping, that sort of thing. Any questions?
Thanks, Richard, for that great talk. We have one question. We are running a bit over time, but I'll just ask this question from the chat. So they ask, if I'm understanding correctly, the Broad-XAI also takes into consideration and assimilates the data of an explanation that is in an order different than the one of the current explanation is trying to solve. If so, what aspects from slide 12 would it compare first? So I guess he's referring to slide 12. Yeah.
Not 100% sure what that is asking.
I guess if I interpret correctly, I think he's asking which of these aspects would it prioritize?
I think probably so this actually isn't implemented yet. It's actually part of the research project I described for the defense. But in the multi-objective sense, we're looking at having these different things like safe or ethical type things as separate objectives. And so the policy that's being followed by an agent can have its primary objective of the goal that it's trying to achieve, a safety objective that it's trying to maintain something. And from that, you get a Pareto front. And you select a policy on that Pareto front. Peter kind of covered this earlier, so I know not everybody here would have been at Peter's talk earlier, but I believe this is recorded, so do have a look at that if you're interested. But you select a particular policy from that front, and then your explanation, it's not so much choosing between these, but you're saying you've primarily chosen your objective, but the reason why you didn't choose the absolute fastest way there or the most efficient way there is because this particular option was to some degree safer than the other option. Because even though the other option may have been faster, this one was safer. And so you sort of trade off between, in your explanation, is trading off between these objectives as to trying to explain what the balance was between them.
All right, thanks, Richard. There is another question in the chat, but I think we're running a bit late. I think we should move on to the next speaker. So yeah, I'd like to thank Richard again for his talk. Thanks very much for sharing.
Send us an email, or me or Francisco an email, and we'll try and answer.
Yeah, it's in the chat. You can look at it.
Yeah. Okay.
Cool. Thanks.
Thank you.
All right.